In an earlier lesson, we learned how to construct perpendicular bisectors. Let's review that briefly and look at the properties of the perpendicular bisector, and then just know that we will extend it to triangles eventually. So if we have a segment and we want to construct the perpendicular bisector, this is the construction where you put the stylus on one end and the compass must be open greater than halfway. So as long as it looks like you've opened more than half the distance, we can swing arcs above and below the segment. It doesn't have to be one connected arc. We're just looking for those two intersection points, but you could go ahead and swing the whole arc. And if we carefully line up these 2 points, the segment that we make, so this segment is the perpendicular bisector, you can see that we do have a right angle there. That's what it means to be perpendicular. This is the symbol for perpendicular, but it did make a right angle. And the original segment that I started with has been split into 2 equal pieces. It bisected it or cut it in half, okay? What I would like to explore, and this is called the perpendicular bisector theorem. Again, we don't really want to worry about the names of these things too much, just the properties. If we put a point on this bisector anywhere, you could put your point in a different spot. Just put a point anywhere on the segment. And then if you take your compass and you measure how far it is away from the endpoints of this original segment we started with, you should see that it's the same distance in either direction. I hit the endpoints of the segment. Let me just try it again. I'll put a point down here. Again, I'm just picking a point anywhere on the perpendicular bisector itself. And if I measure to the end of this segment and the end of the segment, you can see that the distance is the same. It's equidistant from the endpoints. Let's just lightly sketch that once. So if I go from this point to the end point and to the end point, these distances are the same. And that's all the perpendicular bisector theorem says. If a point is on a perpendicular bisector, let's use the symbol perpendicular bisector, then it's the same distance away from the endpoints, right? Then it is, we use the word equidistant. Equa meaning equal distance, the same distance away from, equidistant from the 2 endpoints of the segment. Let's go ahead and name that segment XY, just in case you ever look back at this construction to try and remember what the perpendicular bisector theorem says. You will know. Likewise, it turns out the converse of this is true as well. And remember, the converse is formed by switching the if and the then. So the converse of the perpendicular bisector theorem says, if a point, so suppose that there's a point way out here, and that point, when I measure, lo and behold, that point is also the same distance away from the 2 endpoints. Then that means if I were to go ahead and extend this bisector, that point would be on the segment that's doing the bisecting, on the perpendicular bisector. If a point is equidistant from the 2 endpoints of a segment, then it is on the perpendicular bisector. Of that segment. Okay, so if we had a triangle has 3 sides. You could draw any type of triangle you want. I am quickly going to do one final construction and then we'll call this quits. Let's construct the 3 perpendicular bisectors of the sides of the triangle and just see what we notice, okay? All right, so here we go. I'm gonna go ahead and swing these full arcs so we can kind of keep track of where we are. Let me start with the shortest side. So I just know that the compass, I'm gonna bisect this side, needs to be open greater than half. So I'll swing an arc from that end point and from the other end point of that segment. Okay, once I do that, I'll line up those 2 intersection points carefully and draw the perpendicular bisector. This segment is making a right angle right there with the segment we constructed makes a right angle with that side of the triangle and cuts it into 2 equal pieces. Let's do it 2 more times. So it does kind of start running together. So you have to concentrate as you do this. So we want to bisect this side. We need to open the compass greater than half and swing arcs on either side. But I'm going to swing continuous arcs in hopes that we can see clearly which arcs go with which side. Okay, so we're going to line up this point and this point. And there's the right angle that was promised, and this distance is equal to that distance. We cut that side in half. And now we're going to cut this final side in half. So again, opening my compass greater than half the distance. I want to change it, even though that's greater than half the distance where I had it. I don't want it to overlap what I've already done. So I'm going to go a little bigger, okay? And I'm going to swing arcs on either side. So from there, coming to the other end point, another set of intersecting arcs. And we do have a little bit of a mess. Like I said, you have to concentrate, but it's this intersection point and that one. These are the 2 that we want to line up. And what you should notice, if you've done it correctly, is that the 3 bisectors of a triangle, the 3 perpendicular bisectors, and once again, I do have that right angle right there, and we did split this segment into 2 equal pieces. They all intersect at a single point. Let's just write that. The 3 perpendicular bisectors of a triangle intersect at a single point. That single point has a special name, and we're going to look at this in more detail a little later, but we can go ahead and write the name so you've at least heard it. That point is called the circumcenter.